Hi, year 13. Hope you're doing okay. This is just a little video I'm doing because I'm moving house today when you watch this video. So you'll want to, yeah, I just wanted to show you a few questions to help you get going. What I want you to do today is work through section A, the big integration question. It's got like 40 questions on integration. It's in the integration chapter just after the work we've been doing recently. I wish I could give you the page number, but I don't have a copy of the textbook here. But I know there's a section A with 40 questions on integration, and followed immediately by a section B with 40 questions or 39 on integration. I just want you to have a go at as many of these as possible. Now, you're not going to get 80 done in an hour. I'm not that optimistic, but you'll get a few done, yeah, and you can get lots done. And really, I just want you to practice in this lesson which integration technique to use, yeah, because that's the hardest bit in integration, really, selecting the right method. So what I'll do to help you, now I got this out of the other textbook, the one which we don't have in school, but we have an electronic copy of. And I don't mind if you want to work on this exercise instead, but we might as well use both textbooks, and they're on the side. And if you're in the classroom, you just want to sit there for an hour and work, grab the textbook and work through section A for 40 questions. But here's me demonstrating a few. So I'm just going to basically talk about which technique should I use. So let's get straight into it. 1A. Okay, this is a classic one. I'm thinking straight away ax plus b to the n always integrates to, provided n isn't minus 1, of course, ax plus b, oh, very dodgy handwriting, to the n plus 1 over a times n plus 1. That's what I'm going to use here. So I'm just going to directly integrate 2x minus 3 to the power of 7. And this works with halves or negatives, provided it's not minus 1, it will still work. But I'm just going to increase the power by 1, divide by the new power, and don't forget to divide by this 2 as well. That's just the rule you need. And by the way, you can see it works because at the end, when I've done it, if you're good at quick chain rule in your head, you can see that this differentiates back to what I had up here. Because when I differentiate it, the 8's going to come down, and so that 8 over 16 will become a half, but then the 2 comes out and times by the half to make 1. The power reduces, and so you get 2x minus 3 to the 7. So it does in fact work. Right, what about B? Well, this one, I mean, you probably can do it by parts as well. Often with these ones, you can do them by parts, but I would rather not use by parts if I can at all avoid it. And so this one's saying to me substitution. Actually, I mean, yeah, substitution. Now, and I know Hayden's going to straight away say let u equal 4x minus 1. He always gets the good substitution, Hayden. He's got a great rule for it. Don't know how he does it, but he always picks the right substitution. And then we're going to do du is 4 dx. I hope you don't mind me timesing the dx straight over there. And I'm actually going to rewrite that as a quarter du equals dx. The reason I'm going to do that is because I've got no 4 dx in there next to each other anyway, because it's in a square root. I can't use it. And now I can rewrite the integral as, okay, x is u plus 1 over 4. That's the x term. And then root 4x minus 1 is just u to the power of a half du. Yeah. Have I put my quarter du in there? No, I haven't. I put the du in there, but I didn't put the quarter in there. So that quarter du is swapped with dx. I can take a quarter out actually and make that 1/16. And then it's going to become u plus 1. I should have used brackets there more judiciously, times by u to the half. And what we can do is we can just multiply that out. Sorry for my handwriting here, it's getting really bad. It's hard doing it when you can't see where you're writing on the graphics tablet. This is going to become u to the 3 over 2 plus u to the half du. And then we get 1/16 u to the 5 over 2 times by 2/5 plus u to the 3 over 2 times by 2/3. Now they probably won't write it down like this in the back, which is kind of annoying. So let's write it down how they would do in the back. They'll probably take out, well, they'll probably add the fractions together. And that will give us, okay, what's that? 6 plus, well, 6u to the 5 over 2 plus 10u to the 3 over 2 over 15 plus c. And then what we can do is we can take out the u to the power of 3 over 2. This is the hardest bit, to be honest, in these ones. It really is. It's a fair bit of work you've got to do here. So I've taken that outside, and then I've got 6u plus 10 over 15. And as I recall u is 4x minus 1. And so what I can write that down is 6 times 4x is going to be 24x. Then we're going to have minus 6 plus 10. So that's going to be 4x minus 1 to the 3 over 2. I'll write that down first. Over 16 multiplied by, okay, that gives you 24x minus 6 plus 10. So that's 24x plus 4 over 15. Yeah. And they probably write that down in the back as 4x minus 1 to the 3 over 2. They probably take out the factor of 4 and cancel it with 1 to the 16. So that will be 6x plus 1 over 4 times 15, 60. Yeah, plus c, because I've suddenly ignored that. Sorry about that. I dropped it there. Cool. So that one was a bit of a pain at the end. I reckon that's the way the answer's written in the back. Okay, let me quickly demonstrate. See, this one is lovely. It may not look lovely, but it is lovely. Some of you will prefer to use a substitution, let u equal cos x here, or let u equal sin x. Actually, let u equal sin x is probably easier. But actually, I prefer to recognise that this is of a special format. Maybe I will use substitution, but this is actually of the form f dash of x, f of x to the n. And I'm always on the lookout for those kind of integrals because you can just integrate it straight away to f of x to the n plus 1 over n plus 1 plus c. But let's say you didn't spot that. Let u equal sin x, then du equals cos x. And I hope you don't mind if I times the dx straight over here. Because look at this. I got cos x dx. And so this is just going to become u squared du. And so you get u cubed over 3 plus c. And that's the same as sine cubed x over 3 plus c. Now that's exactly what this formula is telling me I should get, because cos x is a derivative of sine x, and sine x is to a power. Sine x is up my f of x here, cos x is my f dash of x. Sine n is 2. That's going to give me sine x cubed over 3 plus c, which is exactly what I got. But yeah, two ways of thinking about that one. Okay, D, x ln x. I'm afraid it's by parts for you, x ln x. There's no way of doing it other than by parts. Now, you're tempted to say u equals x, and most of the time in by parts that'll work. But if there's a ln involved, well, you have to let u equal a ln x, basically. And dv by dx will be the x. And so you're going to get du by dx is 1 over x. V is going to be x squared over 2. We're going to apply the formula. The formula is uv, so that's that times that, x squared over 2 ln x. That's the formula uv minus the integral of v times du by dx. That's essentially the by parts formula. Minus the integral of v times du by dx. Well, actually gives us x over 2 after simplifying. And so now I've got it. Let me just get that out of the way. I'm going to have x squared over 2 ln x minus x squared over 4 plus a constant c. And it's done. Oh yeah, I'm now on E. Look at this one. Look at this one. This one looks menacing. Yeah, and when they look menacing, maybe there's a trig identity which can help you. You know, that's what I'm normally thinking. Straight away, with 4 sine x cos x, I'm thinking that's the same as 2 sine 2x. Yeah, because 2 sine x cos x is sine 2x. And with the bottom, I'm thinking, isn't that double angle for cos? Because 1 minus 2 sine squared x is cos 2x. So surely 4 minus 8 sine squared x is 4 cos 2x. And so I can change the bottom. I can also change the top to 2 sine 2x. And look at this. Thanks to that, I can see I'm really being asked to integrate a half tan 2x. Now, tan 2x is in the formula book, yeah? You can just look it up. And it actually integrates to... Now, don't forget to divide by this 2 as well. So it's going to become a quarter ln sec 2x plus c. And they normally condone it if you don't put the modulus sign in. Just check always with these that it does actually differentiate back to a half tan 2x. The 2 is going to come out. We're going to get 2 over 4. Ln of stuff is going to differentiate to 1 over the stuff. So I've got a half times by 1 over the stuff. But I'm also going to have to differentiate sec 2x, and sec 2x differentiates to sec 2x, 2 sec 2x tan 2x. And that gives me, after I've cancelled that, well, I'm getting tan 2x there, which worries me because it implies that I have made some kind of mistake, because I should be getting half tan 2x. So let me just quickly check again. I integrated it. Tan 2x differentiates to ln, sec 2x. Let me just check my differentiation again. When I differentiate inside the function, oh, I'd already got the 2, I think. Yeah, so differentiate inside the function, you're going to get a quarter times 2 sec 2x tan 2x. Now differentiate ln of stuff, you get 1 over the stuff. Yeah, and this works out right because you do get a half. Good. Sorry, yeah, I don't know what I was doing before, but something clearly went wrong. And that differentiates back to that. Okay, question F. Let's do F now. Okay, this one is one of those ones where the bottom nearly differentiates to the top, because wouldn't it be nice if the top was a 4 or -4, or even better, because then the bottom differentiates to the top. So what I'm going to do is I'm going to write -4 there, which is cheating. And so I'm going to put -1/4 outside to compensate, because -1/4 times -4 makes a positive 1. And so the answer is -1/4 ln of 3 minus 4x, and you've finished, plus c. Now, I could do some more for you, but I think it's probably best that you have a go at the Section A questions. Like I say, Section A, large integration question, large section on integration. Could you have a go at as many of those as you can possibly do in the hour? Any ones you just get absolutely stumped on, you let me know next lesson, yeah? And we're going to work through them together. But don't waste this hour. Have a really good go at those questions, and best of luck with them. I hope they go really well. And yeah, please, any questions you can't do, bring them to the next lesson and we'll get them sorted out then. Best of luck with this. I hope that was useful. And yeah, keep up the hard work. Bye-bye.